Hello dear friends, welcome to the lecture of differential calculus. We are going to study the chapter of mean value theorems. In this chapter we shall study first Rolle's theorem, then Lagrange mean value theorem and Cauchy's mean value theorem, and problems on it we shall study and their different forms. So first we shall study Rolle's theorem. I have written a statement, the statement of Rolle's theorem. The statement is, if a function f is first continuous in a closed interval a comma b, second derivable in the open interval a comma b, and third f of a is equal to f of b, then there exists at least one value c in the open interval a b such that f dash of c is equal to 0. So this is Rolle's theorem. So before mean value theorems, Lagrange mean value theorem, we are going to study Rolle's theorem because it has one more additional condition than the Lagrange's theorem. There are three conditions we see. Continuous function must be continuous in closed interval ab, closed interval a comma b, and second condition is derivable. The function must be derivable in open interval a comma b, and the third is the values of the function at a and b must be equal, that is f of a is equal to f of b. If these three conditions are satisfied, then there exists at least one value in c in the open interval a b such that f dash of c is equal to 0. So this is the meaning of the statement of the Rolle's theorem. Now we will see the geometrical interpretation after the proof of the Rolle's theorem, but what it says that if we consider the function f, and it must be continuous, means its graph is without break, and the second condition is it is derivable, means the graph or the curve must be smooth, and then the third is f of a is equal to f of b. So that means if we consider the ordinates, f of a will be the ordinate. So this point, see, if we consider this as a, and then if we have this must be at the same level, this is b. So these heights, that is a and b must be equal. So that is the meaning of the third condition. Function's value, this is function y is equal to f of x. The graph we have considered here, y axis, and this is x axis. So the function is continuous, that means its graph is without break, and derivable means it is smooth, or the meaning is we can draw tangent at every point to the curve. That is the meaning of second condition. And third is the values of the function at a, which is this distance, height a, and must be equal to the value of the function at b, and that is b. So if these three conditions are satisfied, then there exists at least one value c between the open interval. We know the meaning of difference between the closed interval and open interval. Here all the points between a and b, including a and b, are considered in closed interval, and in the open interval the end points are not included. So therefore, except the end points, all intermediate points are there in the open interval. So c is some point between a and b. So that means a is less than c is less than b, such that the derivative at that point is 0. So this is the meaning of the Rolle's theorem, meaning of the statement of Rolle's theorem. Now we shall prove the theorem. See here, given that the function is continuous, f is continuous function in the closed interval ab, and by the property of continuous function, f must attain a maximum value and minimum value in the interval ab. So the function f is continuous in the closed interval AB. So therefore there exists a maximum value, say we are our greatest value capital M we will show. Now you see the function is continuous in this interval is AB. So from this interval the function is continuous, means the function has the maximum value and minimum value at some points. So we can see if y is the value of the function, that means height is the value of the function. So here at A, this is the value of the function, and see where the height is maximum, the function is having maximum value. So that means at this point the function is maximum, and we shall suppose that value is m. So this value, this height is m at this point, and suppose that point may be considered as say some point C. At C the function has maximum value, and minimum value you can observe at this point the function has minimum value, and we may write this as m, small m, and suppose the value small m occurs at point D in the interval. So that we shall now write here. The function is continuous, therefore the function, therefore f has the greatest and the least value, has the greatest value capital M and the least value small m at some points C and D. Or that means we have assumed the function has maximum value m at point C. So that is, therefore f of C is equal to m and f of D is equal to small m. So a smaller value occurs at point D. So that we have assumed. So this is the property of continuous function. If function is continuous, then it will attain a maximum value and minimum value at some point, or greatest value and least value at some points. So thus f of C is equal to capital M and f of D is equal to m. Now between capital M and small m, there are see two cases. Either these are equal or they are unequal. So now there are two possibilities. Two cases. First, capital M is equal to small m, and second, or it must be, or second, capital M is not equal to small m. So either they are equal or they are unequal. Now we consider both the cases. First case, if capital M is equal to small m, then what is the meaning of capital M? It is the greatest value of the function C, and small m is the in this interval. The function takes here the height is more, that is the greatest value. If capital M is equal to small m, that means the greatest value coincides with the smallest value. They are equal. Then the greatest value coincides with the least value. What is the meaning of this? The greatest value coincides with the least value means maximum and minimum value are equal, means the function must be constant. Then and only then it is possible. You see, if the function is of this form, here the maximum value is m and minimum value is also the same. So therefore the function is constant, having the same value at every point. So this means then f becomes a constant function. And if f is constant function, then its derivative will be, we know derivative of a constant is 0. Then, or therefore, f dash of c is equal to 0 at every point for all c belongs to the closed interval ab. And because function has the same value from a to b, and at every point the derivative is 0. That means f dash of c is equal to 0 because f is constant, so its derivative is 0. And see, this shows that the theorem is true. What we have to show, if these three conditions are satisfied, then there is at least one, not only one, maybe more value of c, but there must be at least one c such that f dash of c is equal to 0. And in this case we got f dash of c 0 for all c. So there are infinitely many points, or at every point the derivative is 0, hence the theorem is true in this case. In this case means m is equal to small m is equal to capital M. Now we shall consider the second case, that is small m is not equal to capital M, as like this. Here for this case, now this case we have drawn the figure that the function is constant. Constant function has the graph like this. Y is equal to constant f of x. Why f of x is constant means y is equal to some value, say p or d, etc. And then here the graph will be of this type, and derivative at each point is equal to 0, and thus the theorem is satisfied in this case. And now the second case, if capital M is not equal to small m, like this. Here capital M is this value, this height, and small m is this one, minimum height, and therefore these are unequal. Then this, at least one of them is different from f of a and f of b, because f of a and f of b are equal. Then one of them is different from the equal values f of a and f of b. So this is the case, and this either m is not equal to f of a or small m is not equal to f of b, because f of a and f of b are equal. So here both are unequal. See, capital M is greater than this f of a, which is equal to f of b, and small m is less than f of b and f of a. So these are all different values. That is, m is not equal to m and m is not equal to f a. M is not also equal to f of b. So that is the case we have here. So therefore, if this maximum value, that is m, is equal to f of c, is different, so therefore m is equal to f of c is different, or let we instead, therefore we shall consider let m is f of c. We have seen, considered here, m is f of c is different from them. Them means f a and f b. So capital M is different from the equal values f a and f b. M is different from m is equal to f of c is different from f a and f b. So this means c is different from a and b. F of c is different from f a and f b means c is different. Therefore c is different from a and b, and therefore c lies C is certainly between A and B, but different from A and B means C is not equal to A and C is not equal to A, but C is in between A and B. So that is, or we can write A is less than C is less than B. It is an intermediate value between A and B, but not equal to A, not equal to B. And or C is in the open interval AB. We have seen the meaning of open interval. It is except endpoints, the value lies in the interval. C is the interval A comma B, open interval A comma B. Now you see what is the first, up till now we have used the first hypothesis of the theorem. That means function is continuous. Because function is continuous, it has maximum and minimum value or greatest and least value, and that condition we have used. Now what we have obtained there, this point C is in the open interval. And what is the second condition? The function is derivable in the open interval A comma B, and C is in the open interval A comma B, means the function is derivable at C. So by assumption, the function f is derivable at C, or that is f dash of C. And what is f dash of C? In the form of limit. So we have which is limit h tends to 0, or I shall write here. Function f is derivable at C, and therefore f dash C exists. Derivable means the derivative exists, and f dash C exists. And what is the definition of f dash C? We have seen earlier in the chapter of differentiation, the definition of f, derivative of f at C. So therefore f dash of C is equal to limit h tends to 0 f of C plus h minus f of C divided by h. This exists for both h positive and h negative close to 0. For both h tends to 0 from plus, exist for both h tends to 0 from right, h tends to 0 from right, and h tends to 0 from left. So this also we have seen because there are two types of limit, left hand limit and right hand limit, and therefore the derivative is a limit. So there will be two limits, left hand limit and right hand limit, and accordingly there will be two types of derivatives, that is left hand derivative and right hand derivative. And when we have seen, when the derivative exists, if the left hand derivative is equal to the right hand derivative, then the derivative exists, and that means this limit must be the same for h tends to 0 from right and h tends to 0 from left. H tends to 0 from right means h is positive and approaches towards 0, and h tends to 0 from left means h is negative and approaches towards 0. So exist and must be equal for both this. So now we shall see. So thus now f of C is maximum. So we have seen here is maximum value is m. F of C is the greatest value, greatest or maximum value of f. So therefore f of C plus h must be less than or equal to f of C for both h positive or negative values of h. For both positive and negative values of h. What does it mean? C, f of C plus h, in the neighborhood of C, the function's value of at f of C plus h must be less than or equal to f of C. So then we say f of C is maximum. So or otherwise we may see this. We have drawn the graph earlier like this. See, we have the graph as like this, and these values are equal at this point. So this is the maximum value at C, and this height is f of C. So f of C plus h will be, that depends on h is positive or negative. F of if h is positive, C plus h will be this value, and at this value is less than this f of C. So this is f of C, and this is f of C plus h. So f of C plus h is less than or equal to f of C, and if h is negative, then the point will be C minus h. If h is negative, then this is on the left side of C, and for either side the value of the function is less than this. That is why at C it is maximum. So for maximum value the graph is always like this, and this value is maximum. On the right of that value the value is less, as well as on the left of that the value is less than f of C. So in whether h is positive or negative, this f of C plus h is less than or equal to f of C. So that is what we have written for both positive and negative values of h, and therefore we have from this. Now we will obtain this expression for h positive and h negative. So what will be f of C plus h minus f of C divided by h when h is positive? Then f of C plus h minus f of C divided by h for h greater than 0, positive value of h. See, this is less, this value is less, and less, from less value a greater value is subtracted. So that means the quantity is negative. From less value the greater value, this is the greatest, this is smaller, and therefore the quantity is negative, and at the denominator h is we are assumed as positive. So negative divided by positive, that is negative, or we shall suppose this is less than, or we have to write this as less than or equal to 0. Either 0, if these two are equal then it will be 0, and if not it is less than 0. So this is the case for h greater than 0, and we may suppose this as 1. And now what happens if h is negative? F of C plus h minus f of C divided by h. So for h less than 0. Now you see, when h is less than 0, so this is always negative. The numerator is always negative, because f of C plus h is less than or equal to f of C, means the numerator is less than or equal to 0. And what about h? H is negative. So this is negative divided by negative, and the quantity is non-negative. Negative divided by negative is positive, or it may be equal to 0. So therefore we have written greater than or equal to 0. So that is the two cases. From this we have the numerator is either 0 or negative, and if the denominator is positive the value is less than or equal to 0. And when the h is negative, so this is also negative or 0 and negative, that means the value becomes positive. Negative divided by negative is positive, negative divided by positive is negative. So these are the signs we have. And now for h tends to greater than 0, so let h tends to 0 from right, means the first case. Now we suppose this as second one. H tends to 0 from right, then what this the first statement gives, then from 1, what about 1? See, take the limit as h tends to 0 from right, and this limit as h tends to 0 from right is the derivative. See, this is the limit h tends to 0 is the derivative or that will be the right hand derivative. Then from 1, r f dash of c is less than or equal to 0. R stands for right hand derivative. R f dash of c is less than or equal to 0. And let h tends to 0 from left. Then from 2, second relation. What is the second relation? See, this is the h tends to 0 from left means h is negative. So h is positive means h is greater than 0, h is negative means h is less than 0. And if you take the limit for the second, it becomes left hand derivative. Then L f dash of c is greater than or equal to 0. Now we shall suppose this as 3 and 4. But f dash c exists means when the derivative exists, the right hand derivative and left hand derivatives must be equal. And therefore, when 3 and 4 will be equal, only if both must be equal to 0, then they will be equal, otherwise not. Because this is less than or equal to 0, this is greater than or equal to 0. When it is less than 0 and when it is greater than 0, they will be unequal. Equality is for, or common relation is equal to 0. 3 and 4 both are true. The relations 3 and 4 both are true if and only if f dash of c is equal to 0. And what is c? C is, earlier we have written c is in the open interval AB, where c belongs to open interval AB. And thus we have obtained the result of the theorem. That means f dash of c is equal to 0 for at least one value c belongs to the open interval AB. But here we have considered m is equal to f of capital M is equal to f of c. The exactly similar result we will obtain the same result for taking m is equal to f of d and different from f a and fb. We will get the same result by taking small m is equal to f of d different from, instead of capital M is equal to f of c, we have obtained f dash of c is equal to 0. If you take small m is equal to f of d, then in this case we will get f dash of d is equal to 0, and d is again in between a and b. So f of d is different from fa and fb, and this proves the theorem. So hence the proof. We have proved there exist, this proves the theorem. There exists at least one value c in the open interval AB such that the derivative at that point is equal to 0. So now one more thing we shall consider here is the geometrical interpretation of Rolle's theorem. So that is a simple part, and we will have it also. So I shall consider the geometrical interpretation part here. Geometrical interpretation of Rolle's theorem. So what geometrical interpretation means, so what geometrically Rolle's theorem states, that we shall see. Now see, we shall draw the graph of, suppose this is the function, and we may consider the function in any interval, and the shape may be different, or we may consider like this also, and we will see, or we may have like this also. The condition is the ordinates must be at equal height. So this is the point A and this is the point B, and it is at the equal height, and we will have these points A and B. Function is considered in this interval AB, and now function is continuous, that is the first condition. Function is derivable, that means we can draw. The meaning of function is derivable, geometrical meaning of the function is derivable at a point means we can draw tangent. The graph is smooth and we can draw tangents at every point to the graph or to the curve. And now the third condition is also satisfied, f of A is equal to f of B. So f of A is equal to f of B means the ordinates at A and B are equal. And what the meaning of this is, there is a point C such that f dash of C is equal to 0. And what is f dash of C? F dash of C means, we know derivative represents slope of tangent. Derivative represents slope of a tangent, and slope of a tangent, this side is slope of tangent. Slope of tangent at C, and that is equal to 0. Slope of tangent at C is 0, means what? The tangent is parallel to x-axis. Slope of x-axis is 0, we know, and a line which is parallel to x-axis has slope 0, and therefore the tangent at the point is parallel to the x-axis. Now see what are the points from this A to B of the curve, the tangents at which are parallel to x-axis. If you draw tangent at this point, then this will be like this, a line touching the curve at single point. So tangent must be parallel to the x-axis, and we can see easily here that the tangent will rotate like this, and tangent at this point is parallel to the x-axis, and this one point exists. And not only one point, you may observe the tangent at this point also, either maximum or minimum point, the tangent at that point is, and also this point, the tangent is parallel to the x-axis. So this is a minimum value and maximum value in this interval, but if you consider this interval, then this is minimum and this is maximum. If you change the interval, then minimum and maximum value may change. And this is the point we may suppose as C1, this is C2, and this is C3. So thus this is the geometrical interpretation of Rolle's theorem. If the three conditions are satisfied, then there exists at least one point such that the tangent at that point is parallel to the x-axis. That means the curve is without break, the curve is smooth, means we can draw tangent at every point to the curve, and the ordinates at end points, this height A and B are equal, these heights are equal. You may see this, take this point as B, this must be equal. Then there exists at least one point in the interval AB, open interval AB, such that tangents at that point are parallel to x-axis. That is the geometrical meaning or geometrical interpretation of Rolle's theorem. So this is about the statement and proof of Rolle's theorem and geometrical interpretation of Rolle's theorem. In the next lecture, we shall solve problems to verify Rolle's theorem. Thank you.